Hello, and welcome to the second part of my talk about rules and learning. My name is Carmine-Emanuele Cella. I am an assistant professor of composition and music technology at UC Berkeley. So this talk is part of a tutorial for EUSIPCO called Statistical Relational Artificial Intelligence for Unified Music Understanding and Creation. Okay, so this is the second part of the talk called Rules or Learning. In this second half, I'll try to answer the question that I, asked at the end of my previous talk in the previous video. And actually, the answer would be an example. Basically, would be a project that I did for a few years now for music creation that uses somehow a number of strategies and technologies and techniques for handling music information. So before we start, let's see a quick summary of the previous talk. So I was mentioning that music information, one way to handle music information is by handling the relational complexity and the acoustic complexity of music. One key tool to that are projective representations. They are an essential tool used since the beginning of music information, I suppose. Projective representation are actually can be classified in a number of categories, among which the a priori representation and learned representation, and you will have, of course, unsupervised, supervised representations, and all of them can be multi-scale, so they can act on different scales, like time scales or just scales. I gave examples of two projective representations. One is the scattering representation. It is an a priori multi-scale representation. While and the sound types, it is actually an unsupervised multi-scale representation. So the idea is that in the scattering transform, you don't learn anything from data. In sound types, you do learn something in a non-supervised or unsupervised way. The question that I was asking at the end of my previous talk was, can we actually improve this representation by adding some relational information in a more proper way? Like, to some extent, both scattering and sound types use some relational information by having a number of layers, but there is not something like a symbolic kind of logical or rule-based information that we add to this representation to improve the relational complexity, to handle better, the relational complexity in music signal. So that would be basically the question of today. So the question is, can we improve projective representation by adding these kind of rules? So I would like to introduce you a second tool. So if the first one was projective representation, this one is actually constraint optimization. So optimization is a strategy to solve a problem, usually high-dimensional problem, by some sort of cost functions, but we can actually achieve this effect maybe introducing some constraints that we can use to change the way the optimizer solves the problem. In this specific case, we can use even some supervised constraints to improve or help the optimization process. I will give an example of these constraint optimization in the context of a project that is something that is important for me because I've been working on that since 2016 now or something like that. And this is computer-assisted orchestration. So I'll give you an introduction of this problem, and I will show you why computer-assisted orchestration is an example for me of a representation that takes into account both the acoustic complexity of a signal and the relational complexity, at least to some extent. Of course, this was not this was not done by design in this project, but in the end, we added a number of strategies to cope with these kind of complexities. I guess that at the end of this talk, I will ask you another question, actually, that will maybe give set the stage for my colleagues and for next talks of this tutorial. I guess that this will be related to extending the strategies that I will show you in the context of computer-assisted orchestration. But let's see what is computer-assisted orchestration. Well, roughly speaking, we can say that it's a process that searches for the best combinations of orchestral sounds to match a given sound that we call target sound under some constraints. So this picture is actually, an example of that. Suppose we have a number of samples from a database, like for example, clarinet E4 in pianissimo ordinario, and the trumpet B flat 5 and mezzo forte staccato, whatever, and then the violin A6 fortissimo pizzicato. So the point would be that we sum up these samples, and they should sound close to a target sound, like perceptually close to a target sound. So this is actually a complicated problem because of a number of reasons. One is that we don't exactly know what means close in the perceptual sense, like why and when two sounds are perceptually close. That's kind of a question in itself. And then also, depending on the size of the database, you can understand that finding the right combinations of samples of the database can be a very complex problem. Like it could be the search space could be very large. So I will show you the main problems that we face when we try to do this kind of to work on this kind of problem. If orchestration is, we can say that as a projection, so to speak. So we go from one space to the other, like the symbolic space that we were discussing in the previous talk, into the signal space, like the sound, the space of timbre. So how we do that? We just play the score, right? So we have a score, we have performers and the conductor and the instruments, and all together they generate a signal. But the question is behind assisted orchestration is, given a signal, can we actually derive a score? And so this is not actually transcription, right? Because transcription supposes that we have a score in the first place. Like, for example, suppose we have a pianist and that, plays a score, and then we want to take the signal and then retrieve the score. But in a sense, assisted orchestration is a generalization of this concept, because the sound in the first place could be done without a score, like could be a bell, exactly, or electronic sounds or something like that. So there is not a score in the first place. So it somehow generalizes the idea of transcription. But the point is, can we go from the signal space of timbre to the symbolic space of a score? That's interesting to see how these actually connect these levels that we were discussing, in the previous talk, like the acoustic level and the relational level of music. So, in other words, can we use an orchestra to reconstruct a target timbre within a compositional context? Now, let's focus 1 second on this last part of the sentence. Within a compositional context, it means that there are constraints that comes from the composer for this kind of process. So we want to reconstruct a target timbre with an orchestra, but respecting some constraints. For example, which instruments we should use, which dynamics, which playing styles we should use, or can we use the flute and the trumpet at the same time? Sorry. Can we use these notes, or we only are allowed to use these other notes? So this kind of compositional constraints. And so that's why we can think about this problem as a double problem. So we want to best match a target sound, but at the same time, we want to fit some constraints that are specified by the composer. More formally, this is a twofold problem that involves optimization, like combinatorial optimization, that is defined on the timbre space, like on sounds, on the acoustic level of sound. But is also a constraint solving problem that is defined on the variables of musical writing, so like the symbols of musical writing, like, for example, the notes, the instruments, or the durations, these kind of things. Let's stop 1 second and see how we could. So suppose we should solve this problem without any information. Like, one way would be a brutal search, a brute force search, right? So we say we have a bunch of samples, the database, we have a target sound, then we can generate all the combinations of these samples, And then we can have a measure that computes the distance between each one of the combinations and the target sound. We can rank these combinations and pick the first, like the closest to the target sound. But this is true, but there are a number of problems. First, it could be possible that the number of combinations is too big. We cannot really compute them physically. It's impossible. The reason is that, so the number of combinations is actually the power set of the size of the database. So if we have 25,000 samples in the database, this would be 2 to the power of 25,000. That is too much, right? It's a very big number. Then there is another problem. We don't really know what means close, perceptually speaking, between two sounds. So the idea of defining a distance in the perceptual space is also a complicated problem. So there is a general strategy that all these softwares that try to solve this problem somehow follows. And this is the one that I am somehow proposing here with this picture. So we have, as inputs, we have basically three things. We have the target sound, of course. We have a set of constraints that are symbolic, like musical constraints. And then we have a database of sounds. So the search process is divided into kind of sub-processes. The first one is how we generate the combinations. Of course, we cannot generate all the combinations of the sounds in the database because there are too many. So we need to find a heuristics that is able to somehow navigate the combinatorial space in a smart way, so to speak, so that generates the best combinations, not all the combinations. Then we should embed this combination into a feature space that we can use to then compute the distance. But again, if we want to compute the features for each one of the combinations, this would take too much time. It would be too long. So the solution would be to actually generate a forecast, like a possible set of features that describes each one of the new combinations generated by the previous step, but without really computing these features. So it's a kind of forecast of the features. And then when we have this forecast, we can actually compute a similarity measure between the forecast of the combinations and the features of the target sound. We can do that a number of times, and then we would optimize this system so that when this distance is small enough, we can stop the search. This would generate a score. This will generate a number of samples that are actually, nodes into a score. For example, each one, I have to actually add a little bit of information. The sound database is not only sound, but it also comes with, usually it comes with symbolic information. Like each sample would be tagged and you would know the instrument, the note, or the playing styles, or the dynamics, and this kind of thing. So basically, once you select the sample, you also select a number of symbols that you can then put on a score. So the idea is that this process generates a score. So it's a symbolic process. So, but we start from a sound. So we have a sound, we make a search, and we generate a score. That's somehow the general outline of the process. Again, we will not go into too much detail, but there are a number of questions that are not easy to solve. For example, the same idea of how we can forecast the feature, or how we can compute the similarity or the dissimilarity between the target sound and the combination. So just to discuss these two little bit of these two stages of the search. What is a forecast or a prediction of the feature for each combination? So we have a database S in this picture, and we see that each sound can be described by a number of features, like K features, D1, Dk. This we can do that. I mean, we can do this beforehand, before the search. We can just take the database and take our time to compute all the features. Then, when we have a new combinations, instead of summing up the sounds, generate the combination, and then compute the features, we would make a prediction based on the features on the individual samples. Okay, so let's step back 1 second. So this is good if the features are somehow linear, right? So we can actually make a linear prediction if the features are linear. If the features are not linear, then the prediction cannot really be linear. We cannot make a linear assumption of linearity of the prediction if the features are themselves not linear. So this is the first problem. Like, we need to find a way to make a nonlinear prediction of nonlinear features. Then suppose we know how to do that. Then the second problem is how we compute the distance between the features d1 decay of the combination and the feature d1 decay of the target sound. Well, this could be a simple distance, like a Euclidean distance in the feature space d1 decay. But indeed, it turns out that we need to have more refined ways to, take into account the perception of sounds. And so, in fact, it's not a simple distance in the feature space. And we'll see which ways we can, in which way we can compute this similarity measure. Okay, so this research generated a bunch of softwares, among which two very important software that are Orchidea and Orchids. Both of these are designed as client server. So like basically in Orchidea, sorry, the first one, the server was implemented in MATLAB, and there was a client in MaxMSP that the user could use to set the parameter, do the search. In Orchids, that is the dynamic orchestration software, the server was implemented in C++ because it required many more, like speed was an issue in Orchids because the search that is dynamic is now, so there are many more parameters to optimize, so it needed some sort of fast code, so that's why it was implemented in C++, and the interface was still made in MaxMSP. A number of people, researchers, composers took part to the development of that. It's impossible for me to name all of them. I will give you some pointers afterwards, but just to name a few, Grégoire Carpentier and Damien Tardieu were the main researchers behind Orchidea and Orchis, and Philippe Esling and Daniele Ghisi were somehow the main researchers behind Orchids. Now, the point is that I started working on this project a few years ago, and I developed an extension or a new kind of version of this project called now Orchidea or Orchidea. And I would like to discuss these part, like this specific implementation of computer-assisted orchestration, because this will be a way for me to show you how we actually can implement this idea of rules, like relational complexity implemented with rules, especially using this, constraint optimization. So Orchidea is a joint project between IRCAM and HEM, the Haute École de Musique in Genève, and Berkeley, University of California. So these three institutes, I've been in all of them. So I was at IRCAM and then at HEM, and then now I am in Berkeley. That's why this project is a joint project, and it involves not only me, but there are other researchers and composers that are actually developing this project. I will give you links afterwards for all the people, to show all the people that actually work on this project. So generally speaking, Orchidea works in this way. So there is a high-dimensional optimization with symbolic constraints. So there is the cost function, so to speak. We will see the cost functions in detail later. They not only optimize the features in the feature space, but they also optimize and take into account the symbolic constraint. So there will be a sort of soft constraint optimization that we'll see in a second. Then there are a number of strategies to improve this search. There is a pre-optimization stage that uses a sort of pursuit strategy, like a stochastic matching pursuit, to determine the initial population of the search. And then there is, there are other technologies. One of important technology that I use is a neural network for the forecast of the features. As I was mentioning, the forecast or the prediction of the feature is actually nonlinear, so we needed to find a nonlinear model to generate this forecast, and namely is a kind of a LSTM kind of network. And then, the distance, I was mentioning that the distance is not a simple Euclidean distance in the feature space. So I designed a specific distance that takes into account some perception. I will, give you the cost functions later on. And then since Orchidea does dynamic orchestration, there is a way to model time. So we do the optimization in time and frequency. So I optimize for the target sound, but I also keep an eye, so to speak, to the previous steps of the optimization so that I can do some sort of continuous optimization in time. and this is important for the musical aspects of assisted orchestration. Like a score has like lines for each instrument, and these lines should make sense, so to speak. So we needed to take into account the evolution of time, the way time impacts orchestration. Okay, I will somehow show you the highlights of each one of these stages of the algorithm. But the general idea is somehow outlined in this picture. So basically, if you see, we have a target sound. We do some sort of decomposition of the target sound into sub-targets that are somehow static. So the target sound is dynamic, but each sub-target is considered as a static event. Then we embed these sub-target into the feature space. The feature space can be, manually done or automatically done. So I will not go into detail, but there are a number of strategies to do the embedding. And then we have the same embedding that happens to the database on top of the image. And then we have these subspace selection is exactly where we apply the symbolic constraints to reduce the search space. The symbolic constraints come as like formal, in a kind of a formal language constraints that we use to reduce the search space, and we also use them into the fitness. So you see that there are two arrows starting from the symbolic constraints symbol. One arrow goes to the subspace selection. It is a kind of a static pre-optimization selection of the search space, and then there is dynamic kind of stage of symbolic constraint that is actually used in the fitness of the search. The search itself is made by two components. One is a pre-optimization stage that uses a specific version of matching pursuit that I call stochastic matching pursuit, or k-stochastic matching pursuit. I don't think we have time to go into detail, but there is a paper that I will give you at the end of the talk so that you can check the details. And then there is an evolutionary optimizer, like a genetic kind of optimizer that uses the principle of genetic optimization, like crossover, mutation, and so on. That does the optimization. So at the end, we select a number of candidate combinations, and then we apply these temporal continuation to make a continuous orchestration, and this would generate our scores. And then we can also generate the acoustic simulation. Since we have the samples in the database, we can actually play the score. We can generate the outcomes would be two. In this case, would be the score, the symbolic score, and the acoustic simulation of this score. Okay, so let me give you a few elements of this process. So evolution optimization, again, is based on the classic genetic operators of crossover, mutation, and I add a stage that I call sparsity, that is a way for the optimizer to drop samples in the optimization. The reason for doing that, specifically the sparsity stage, is that suppose we have a very high-pitched sound, like a whistle or something, and suppose that in the orchestra we have a double bass and a bassoon. Probably these two instruments will not really add something to the final solution because they are, very low, usually in pitch. I mean, the highest pitch of a double bass is pretty low compared to a very high-pitched sound or whistle. So the optimizer should be able to drop this instrument from the solution, and that's what sparsity does. So another parameter for the optimization is actually sparsity. So we want the solutions to be sparse to some extent. So the whole project, the whole optimizer works with a specifically designed fitness or cost function that takes into account a number of things. One is indeed the target sound. So we want to have a spectral distance between the target and a combination. And then there are other components that I will detail in a second, and then we will see how these components will go together for the final cost function. So the first part of the cost function is the spectral cost. So we see here the distance is computed like a difference in the feature space between the target sound and a combination. But there is a kind of asymmetric way of putting weights on this distance. So basically the idea is that if the combination overshoots the target sound, then the penalization is bigger than when the combination undershoots the target sound. We see in the picture here, like the orange lines are actually cases in which the combinations overshoot in the featured space the target sound. And this is actually bad for us because it means that we usually introduce new components in sound, like new partials, for example. And this is bad, is worse than having less partials, so to speak. So that's why we do this kind of non-symmetric kind of distance in the feature space. There's a second part that is the one that is important for our talk, like the symbolic constraints, because if you remember, in the previous talk, I was mentioning this idea of relational complexity and acoustic complexity. So if the spectral cost takes into account somehow the acoustic complexity, then the relational complexity is taken into account by this step, the symbolic constraint, so the constraint optimization. The idea is simple. Basically, we have a sum of costs. The costs are specified as formal sentences, so to speak. And then we penalize the solution if the formal sentences are false somehow. An example of this process is like when we have, what we see here is an example of a target spectrum, a target sound. And we see that there are a number of partials that are maybe above a given threshold. So we associate each partial to a node, and then we use only the samples in the database whose fundamentals corresponds to these partials. So I call that partial filtering, and the idea is that we ask the composer to specify this symbolic constraint, that is, only allow the optimizer to use pitches that we already have in the target spectrum. And so basically, it's a way to select the pitch classes that will be allowed into this orchestration. So the point is that this specific stage of the optimizer is taking into account symbolic constraints. It is a way to deal with relational complexity in music. So specifically, we can, in this specific example, we can select only some notes. So we can just select few pitches. Or there are many other ways, other examples I could show you, in which, for example, we allow only specific combinations of instruments. So we say never have a flute when we have a trumpet, or only have two cellos and a double bass, and never two cellos and a clarinet, something like that. So whatever symbolic constraints you want to specify. So it's kind of a way to tackle the relational complexity of musical writing. But we will see that is not enough. But so let's move on for a second. So again, we don't really need to go into detail, but the point is that when we develop these systems for making the prediction, of course, linear prediction, like a simple sum or weighted sum, was giving an error that was consistently increasing when we increase the number of mixtures. So when we have like 30 samples together, like 30 instruments in the orchestra, then the prediction is so wrong that we cannot really use it. So that's why we need to have a better prediction model, and this finally ended up being an LSTM based neural network to do the prediction of the features. Then the last stage is temporal modeling. So basically the idea is that we have a target, we cut the target into segments. Each segment is individually optimized, but while we optimize each segment, we also optimize the continuation of segments in time. So basically, it's like optimizing a graph in which we look for the closest path between 2 points. So basically, this is the last bit of our cost function. That is, I call it hysteresis of the orchestration. So it's a memory or previous orchestration. So we not only keep an eye on the target, we also keep an eye on the previous solutions of the orchestration of the optimizer. And this is meant to implement a musical principle called dovetailing that we see here in the picture. So the idea is that we want to maximize the continuity in time. So we want to have instruments that overlap in the pitch sense. So in this case, the oboe and the violin, so you see in the first 2 measures, we see a melody played by a single instrument, like the viola in this case. In the last 2 measures, we see the same melody, scattered across a number of instruments, but there are pivot points or pivot notes that actually are played together. So this kind of continuity, for example, the F in between the oboe and the violin, or the D between the oboe and the flute, and so on. So in order to implement that, you need to have a memory of what was happening in previous stage, and that's why we implement this kind of hysteresis. The hysteresis is indeed a spectral distance, the integral of the spectral distance in previous time points, multiplied by the current solution. So it's basically an inner product of the current solution and the previous solutions. So in other words, is a projective representation, these hysteresis of the orchestration. When we put everything together, we have a long cost function that is made by basically 4 components. One is the spectral distance, so the target distance, the one that is asymmetric, that takes into account when the solutions and when the combinations overshoot or undershoots the target. The second part is a constraint, a set of constraints, symbolic constraints. The third part is the memory or the hysteresis of the orchestration. And finally, there is a regularization term that tends to give a priority to sparse solutions. So this is kind of a L1 regularization type of thing. So we use that to sparsify the solution. So there is, of course, you can, there are weights, these lambdas are weights, and there you can control how much each one of these components act in the final cost function. Okay, let's step back 1 second and think about this, what's happening here. So the idea is that we have a number of things acting together. There are projective representations, like we have the embedding of the sound, and we compute a distance on this embedding. So this is kind of the more part of the cost function that relates more with the acoustic complexity. And then there is this constraint. There are the constraints that actually deal more with the relational complexity. And then there are the hysteresis and the regularization. So in some sense, this process is optimization that also uses constraints and uses memory and sparsity to improve the solutions. These joint actions of these 4 components enables the optimizer to somehow take into account several aspects of musical signals to improve the quality of the solutions. Of course, this is kind of a partial approach, is not complete, or it doesn't take into account many other things. Like, for example, there is nothing about, harmonic rules, for example. I mean, there is a little bit, you can state harmonic rules as constraint in the optimizer, but there is nothing specifically designed for musical rules. So I guess this is somehow the pathway to our question for this talk, to end this talk. Okay, so Orchidea is implemented as a template library in C++, and you can download it from my GitHub. It's not open source yet, but it will be very soon. And so it's an API that you can actually integrate in your own applications. And then there are a number of things. So is also deployed. So there is a website that is www.org-idea.org, in which you can find examples and the deployment of the softwares. And the software comes in different flavors. One is a Max package. So it's a bunch of externals and Max patches that you can use for your own, orchestration tasks. The idea behind the package is to allow composers to actually generate a kind of a pipeline for the orchestration depending on your own problem. So in a sort of language of the orchestration, so to speak. But it also comes as a standalone software. So this is easier to use. So you basically drag and drop the samples, and these will be replaced by their own orchestrations. But this is some sort of monolithic approach in which you have less, flexibility in designing the system. So, but nonetheless, this is pretty handy for composers that don't really want to use Max as a system. Okay, let's wrap up. So I'd like to somehow conclude a little bit. So let me open again my slides. Okay, I'm not sure I can conclude anything actually, so it's not real, these are not real conclusions, but I'd like to again ask you another question, and this would help us setting the stage for the next talks of these tutorials. And so Orchidea, it's a mix of things. So you use projective representations, supervised learning, combinatorial optimization, constraints. We take somehow into account for relational and acoustic complexity to some extent, at least. But my question is, can we also improve that? Like, is it possible to create even a more powerful representation that embed relational and acoustic complexity even better, like using a specific language for relational and acoustic complexity? That's the question I have in my mind now. So I guess that to answer the question, we should probably, see what will happen, what will come in this tutorial. But before doing that, let me give you some sort of take-home message. So what we saw is that constraint optimization is also an important tool for music processing because it takes into account, to some extent, or at least it can take into account, relational and acoustic complexity. But I think that the properties that you put into representation, you remember we've discussed in the previous talk about stability, invariance, and uniqueness, must be appropriate to the problem you want to solve. So in the case of Orchidea, we needed some sort of properties, like we wanted to have the representation to be unique, we wanted it to be stable to some transformation. So I guess that when you design a representation, it's because you have in your mind a specific problem that you want to solve. In Orchidea, we use handcrafted features. I didn't talk about that, but indeed, the embedding comes as a long string of features, including handcrafted features, for example, MFCCs, and they are important. So today, we tend to forget what we learned. Like MFCCs are beautiful. I mean, they are designed in a very clever way, and they encode a lot of knowledge, right? So I think that we should use this knowledge while we design new models. We don't need to start from scratch. So the same idea of thinking about end-to-end networks that magically solve all our problems, I think it's not a completely good idea, because I believe that still we want to understand what's going on. We don't really need to just solve the problem. So in this sense, deep learning is a tool that puts together a number of things like representations and optimization, but must be used as a tool, as a component of a larger context, like in which we also know what's going on. Like, my idea is that we want to design a system in which one step of the system or multiple steps can be neural networks indeed, but they are actually solving a specific problem that is framed by our knowledge. That's a statement. I'm not sure if it's really important or not, but my own research is driven by this approach. So I usually tend to design systems in which my prior knowledge is actually useful to design the system itself. It's not just by adding more samples, adding more layers, or increasing the size of the optimizer or something like that. So and then the final take-home message, I think, is that the musical rules are complex, and we must handle that at a logical level. Like, statistical learning is not enough to discover the kind of rules. Imagine the complexity of the Bach's fugue, or imagine the complexity of an orchestration in which you want to have specific combinations of instruments, you want to have specific evolutions in time of the instruments, and so on. I don't think, my sense is that we cannot really solve this example just by brute force learning, statistical learning, but we need to increase the chances of defining and designing this system using logical rules. That's why I believe that one possible framework for designing systems for music information and music processing is indeed the so-called statistical relational artificial intelligence, or StarAI. This will be the topic of the next talks by my colleagues, and you will see how you will see examples of how powerful is this infrastructure and this framework. The general idea is that we should mix together relational behavior, relational rules with statistical learning. So in a kind of in a unified context with a unified language. I believe that this is important for music processing, and I am curious to see where this will go. Actually, my colleagues will show you specific examples, like I suppose chord classification or other MIR related tasks. But I believe that even for musical creation, these can play a role in the future years. Okay, let's conclude by showing you a couple of references again. So there's one paper by Helene-Camille, Crayencour, and me about the idea of mixing together these levels, like learning, probability, and logic, and maybe eventually design a unified approach for music information retrieval. Then I'd like to point you to a paper that I wrote last year, no, this year actually, that is about the relationship between contemporary music and music information retrieval. I call it a successful failure, because music information retrieval generated a lot of research and a lot of results, but to some extent I didn't really manage to use these results in my own creation kind of process, like when I act as a composer, not as a researcher. But so maybe this could be an interesting reading for you. And then finally, there is a paper about Orchidea itself, that is a system for computer-assisted orchestration that is dynamic, and this has been submitted at the moment of this talk, and is under review, so it will come out eventually in the next few months, hopefully. Okay, I think I can stop here. Let me see. Okay. I hope this was interesting for you. This was just, an introductory kind of discussion about the importance of rules and statistical learning for modeling music information. My colleagues will take over and will give you an example of, this kind of process. Okay, thanks so much for your attention, and see you soon.